Welcome to our lecture online, and now let's talk about things such as power and luminosity when it comes to stars. And not only that, in this video and the future videos coming up, we're going to talk about power, luminosity, intensity, apparent magnitude, absolute magnitude, brightness, and bolometric magnitude. Because those things get often mixed and very confused, and I've seen on the internet that these terms are not always correctly defined. So here we're going to try and clarify what these things mean. And we're going to start out by talking about power and luminosity. And in actuality, power and luminosity are really exactly the same thing. Although the term power is mostly used in physics, and luminosity, when it comes to astronomy, that's where it's usually used more often. So power is, by definition, we use the letter P, is simply the ratio of the amount of energy output per unit time. And so the energy output is usually in joules, and the time is usually in seconds. So a joule per second is a watt. We say W for watt, or we use simply the terms watts. And so the power output of something is how much energy something puts out is in terms of watts. And so when we have the sun giving off the energy towards the earth, and of course all of the space around the sun, we can say that the power of the sun, so the power of the sun is equal to 3.9 times 10 to the 26 watts. That's how much energy the sun puts out. That's how many joules per second the sun emanates every single second. And the sun emanates most of that power in terms of visible light. Oh, and I'm missing a T right here, visible light, UV and infrared. A large portion of the amount of energy coming from the sun is indeed in visible light, but a significant portion also is in the infrared and in the UV. So when we talk about the power output of the sun, we talk about all the various energy frequencies, UV, visible light, and infrared, that the sun puts out. Now in astronomy, rather than talk about the power of a star, we tend to talk about the luminosity of a star. And just because we use a different word, luminosity, it is also the energy per unit time, exactly like power, energy per time, and it's also expressed in terms of joules per second. And of course, joules per second is, of course, watts. So the luminosity of stars is expressed in terms of watts, how many joules per second they emanate, and also they talk about all the various energy frequencies or energy wavelengths, UV, visible light, infrared, and some stars may even put out radiation even at higher frequencies, but typically it's in these three frequency bands. So we talk about the power, we can also talk about the luminosity of the sun, which is equal to 3.9 times 10 to the 26 watts. And so you can see that it's really the exact same thing. So astronomy talks about luminosity, power. In physics, we talk about power. Now, it talks about how much energy an object puts out. So how much energy do we receive on the Earth? Well, that depends upon how far it is between the sun and the Earth. The farther we go out, for example, the amount of light or energy received from the sun at Mars is much less than what we get on the Earth, because it's farther away. Since it's spread over a larger and larger area, as the energy spreads out into space, the farther you are, the less of it that you will receive personally from that particular star, in this case from the sun. Well, that has to do with something different. That has to do with the intensity of the energy that we receive, and we'll talk about that in our next video. Here we just have to realize that power and luminosity, in essence, is exactly the same thing. We use power in physics, luminosity in astronomy, and it's simply how much energy an object puts out per unit time, how many watts that object puts out. And so that's how we can tell the difference between those two terms. Now in the next video, we're going to include the term intensity and see how that changes things. And then we'll talk about the term brightness. And once we have those four terms figured out, then you have a pretty good understanding about how stars emanate energy and what the terminology means. So stay tuned if you're interested in this. Welcome to Lecture Online. In the previous video, we explained the difference between luminosity and power, and actually we found that there was no difference at all, that luminosity and power is exactly the same thing. We use power in physics and luminosity in astronomy to describe how much energy a star or any object puts out. How much energy per unit time, I should say. And that's usually in terms of watts. For the sun, the power or the luminosity is equal to about 3.9 times 10 to the 26 watts. Slightly more, but that's a good estimate right there. So, what do we mean by intensity? How does that relate to the luminosity? Well, the intensity of the energy that we receive from a star depends upon how close or how far away we are. The farther away we are, the less intensity, the less intense the light will be. And the way that works is that you can see that as you go farther and farther out, the amount of light coming from a certain area of the sun will spread out over larger and larger and larger area. So as the light or as the energy spreads out over a larger area, each area then only receives a smaller and smaller portion of it. For example, if we're at this distance, let's say a distance of r away from the source, a certain area gets a certain amount of light, and therefore we call that intensity. Intensity is in terms of, and let me write the equation, intensity is equal to the power per unit area. So it's over how much area does that power spread out? Or in astronomy, I guess we can say that the intensity is equal to the luminosity divided by the area. So as you go farther and farther out, the energy spreads over a larger and larger area, so each area gets a smaller and smaller amount. It turns out that the intensity is proportional to 1 over the distance squared. So if you double the distance, you only get a quarter of the intensity. If you triple the distance, you only get 1/9 of the intensity. And that's what I try to illustrate here. So you can see that at a distance r away from the sun, your intensity will be what we call I sub naught. It'll be a certain intensity. But if you're twice as far away, the intensity is now 1/4 the original intensity, because the light now has to spread over an area that is 4 times as big. If you're 3 times as far away, then you only get 1/9 of the original intensity, because all the light that goes through this area right here now will go through a much bigger area that's 9 times as much. So the light or the energy is now spread out over 9 times the area, so you only get 1/9 of the intensity. That's what we mean by the intensity is proportional to 1 over the distance squared. You double the distance, 1/4, triple the distance, 1/9, quadruple the distance, you get only 1/16 of the intensity. So the way to then figure out what the intensity is of the light that you receive, or I should say the energy that you receive, you take the total luminosity of the object and divide it over the area over which it spreads. And of course, the area over which the light spreads is basically a sphere, because it goes out in all directions, radially in all directions. So the light spreads out in a larger and larger and larger spherical shape. And so by the time the light gets to the Earth, you can imagine a sphere that has a radius of the distance between the sun and the Earth, which would be, of course, 1 astronomical unit, or about 150 million kilometers. So if you want to find the intensity at the Earth, what you do is you take the total luminosity of the sun and you divide it by the total surface area of a sphere made by the Earth's orbit. And so it would be 4 pi times the radius between the sun and the Earth squared. Now, a very big distinction here is when we talk about intensity and luminosity, we do talk about the energy coming from the star in all frequencies and wavelengths, not just visible light, but also UV and infrared. Because some stars, they give off more UV energy, some stars give more infrared energy, some stars are more centered around the visible light. So regardless of what the wavelengths or frequency are that the star emits the energy in, we take all of that energy to get the total intensity. By the time the light reaches the Earth, or I should say all of the energy reaches the Earth, again we think of it as light, but in essence it's light, UV and infrared all combined, the intensity of all that energy is around 1361 watts per square meter. Now that's of course when it reaches the upper end of the atmosphere. Once the energy begins to go into the atmosphere, you realize that most of the UV is held back by the ozone layer, and some of the energy is held back by the cloud cover, and then the dust and the particles in the air and the water vapor in the air, and all that holds it back. So by the time the light finally reaches the surface of the Earth, it's probably down to about half of what it normally is, about 700 watts per square meter. And then of course on cloudy days when the sun really holds back more of the energy, the atmosphere and the clouds, then it may be less than 700, may only be 600 or 500 watts per square meter of energy that the surface of the Earth receives from the sun. But at the very top of the atmosphere, when the energy reaches the Earth, we can say that the intensity at that point is about 1361 watts per square meter. You might have seen different values. The original value was more around 1366 or 1367, but with new measurements and calibration, we've narrowed it down where we feel that this is the more correct number. Again, in science, it's never quite absolute. There's always some variation depending upon the measurements and the ability to actually measure these particular values. So hopefully that gives you a good idea about what luminosity and intensity is. And as you continue to watch these videos, you'll get a better understanding of all the various terms in relation to each other, especially when it comes to the term brightness, because brightness and intensity are not the same thing, and you'll see that on the next video. Welcome to ilectureonline. In this video, we're going to explain the difference between luminosity and brightness. Now, we already knew from a previous video that luminosity and power is really the same thing. It's the amount of total energy a star or any object puts out. We can even talk about things that radiate energy, like a brick that's hot and radiates energy. We can measure the power, the total energy coming from the brick. But in that case, most, if not all of that energy will come in the infrared, none of it in visible light or any other frequency. So the total power or the total luminosity is the energy coming from an object in all frequencies, in all wavelengths. So when we talk about the sun's output, we have to realize that part of it comes to us in the UV, part of it in visible light, and part of it in the infrared. What percentage will come from us in each of those categories? Well, with sunlight, about 4% of the radiation that we receive from the sun is UV radiation, about 43% is visible light, and about 53% is infrared. And I do say about because it may be off by 1 or 2 percentage points. So when we now talk about the luminosity of the sun, we talk about all the various frequencies, all the various wavelengths, all the various type of radiation, UV, visible light, infrared together, is the total luminosity of the sun. But when we say how bright is the object, then we talk about the radiation that we can see with the eye. And the only radiation we can see with the eye is visible light, which is only 43% of the total. So when we talk about the brightness of the sun, we only talk about the portion of the radiation coming to us from the sun in the visible light portion, which is only 43% of the total luminosity of the sun. So when we say brightness and luminosity, we definitely mean two different things. Brightness means the total radiation coming to us per unit time, the total amount of energy per unit time, the total number of watts coming to us in the visible light range. And when we talk about luminosity, we talk about all of the radiation coming to us in all the various wavelengths and frequencies. So that varies from star to star quite a bit. For example, Sirius is the brightest star in the sky. That's because it has a very high proportion of its energy that it radiates in the visible wavelength. Now, Betelgeuse is not as bright in terms of visible light, so we can say the brightness of Betelgeuse is less than the brightness of Sirius, the way at least it appears to us. We should say the apparent brightness, because obviously Betelgeuse is a much bigger star and puts out a lot more light and energy than Sirius. But as it appears to us from our vantage point on the Earth, Betelgeuse puts out less visible light per unit area by the time it reaches us compared to Sirius, and therefore Sirius is a brighter star than Betelgeuse. However, if we take all of the radiation combined, the luminosity of the light that reaches us, the intensity of the light, the amount of energy per unit area when it reaches us, is far greater for Betelgeuse than Sirius, because Betelgeuse puts an enormous amount of radiation out in the infrared that we can't see, and Sirius doesn't do that. So we'll get some more detail on that later. But now what we need to understand is simply the difference between luminosity and brightness. Brightness only addresses the visible light portion alone. So the brightness is determined by how much visible light we can see from the object, or how much visible light in this case is emanated from the object. That may be a better way to say it. And the luminosity is all the energy emanated from that particular object. Now let's go back to the concept of how much light do we actually receive on the surface of the Earth. Well, at the top of the atmosphere, the intensity of all the radiation coming to us from the sun is about 1,360 watts per square meter. But by the time that light makes it to the surface, assuming there's no clouds or anything like that, just a plain sunny day, then the amount of energy or the intensity that reaches the surface of the Earth is about 1,050 watts per square meter. Now, because some of that light is being scattered around because of the atmosphere, we also have some indirect light reaching the Earth from the sun. So when we add the direct light, which is 1,050 watts per square meter, and some of the scattered light that also reaches the surface, the total is about 1,120 watts per square meter. Now in the next video, we're going to try and convert that energy that we receive from the sun in terms of lumens, the brightness that we detect on the surface of the Earth. So we already talked about the brightness of a star as it leaves the star. This is the total amount of energy leaving the star in the visible light range. Now what does that mean about brightness when it reaches the Earth? We have a terminology for that. We use lumens and candelas for that, and we'll explain to you in the next video what that really means, what lumens and candelas means, which is a direct conversion of the brightness of the sun, the amount of energy that the sun puts out at the visible light range, and what that means when the light finally reaches the earth in terms of how much energy or intensity reaches us in terms of the visible light range alone. So if you're still interested, keep looking, and we'll have another video for you next. Welcome to Lecture Online, and now we're going to take a closer look at what we really mean by brightness in two ways. The brightness of an object, the amount of visible light that an object puts out per unit time, or the amount of luminosity, only the portion of the visible light luminosity a star puts out per unit time. Or we're also going to talk about brightness in terms of how bright does it appear when it reaches the earth. And in that case, we talk about lumens, or that's related to luminosity. But again, we have to be careful because luminosity defines the total amount of energy that a star puts out, and the brightness that it appears on the surface of the earth is only in terms of the visible light portion of that spectrum. So the terminology may get a little bit confusing, so let's try to make it clear. Again, in summary, we know that the radiation coming from a star spans typically three different kind of radiation bands: UV, visible light, and infrared. And depending upon what star we're dealing with, a greater or smaller portion of each radiation band will be emitted by that particular star. Like a red giant, for example, will put way more of the energy out at the infrared. A star like Rigel, which is a very hot star, will put a lot more radiation out in the UV. The sun here puts out about 43% out at visible light, 53% at infrared, and about 4% at UV. So when we talk about the luminosity of the sun, we talk about the total energy per unit time in terms of watts that the sun puts out. 3.9 times 10 to the 26 watts is the luminosity of the sun. But the brightness of the sun is only determined by the portion that is put out at visible light, so the brightness would be this number times 43%, which is a little bit less than half. Now, how bright does the sunlight appear when it reaches the earth? Well, remember, by the time the total energy reaches the earth, it comes in at 1,361 watts per square meter. Of that, about 1,050 makes it through the atmosphere, so about 320 watts per square meter get held back by the atmosphere. This is on a sunny day, not involving clouds or anything like that. And part of the light is being scattered out, but still makes it to the surface in an indirect fashion. So if we include the direct and the indirect sunlight reaching the earth, it's about 1,120 watts per square meter. Now, of the direct sunlight that reaches the earth, we can say that 1 watt of that sunlight, 1 out of 1,050 watts, produces 93 lumens. That's the energy, that's the luminosity term, or the brightness term. Brightness term may be a better term to use, of the sunlight when it reaches the earth. How bright is the sunlight? Well, we can say for every 1 watt per square meter that reaches the earth, we receive 93 lumens. If we multiply 1,050 by 93, we get about 98,000 lux, which means 98,000 lumens per square meter. That's the brightness of sunlight in terms of the visible light that we receive. Now, a lumen can be defined as a candela per square radian. Wow, what is all that? Well, a candela is a fancy word for candle, the amount of light a single candle puts out. So what that means is that the brightness of the sunlight when it reaches the earth is the equivalent of 98,000 candles shining per square meter surface. So the sunlight is extremely bright compared to the light of a single candle, for example. And that's really where the terminology candela or candle comes from. It's the light put out by a candle. Now notice that a candela can be converted to standard units in terms of 1 over 683 watts per steradian. So the brightness of a candela, or candle, the light of a candle, can be expressed in terms of watts per square radian. A steradian is a square radian, so that either we can write it like this, a radian squared, or a steradian. How do we find a steradian? Well, if we take the surface of a sphere, the portion of the area that is a steradian can be defined by the radius squared. So if we take a sphere that has a radius of r, and the portion of the surface that is equal to the radius squared, that is called a steradian. And since the area of a sphere is 4 pi r squared, let me write that down. So the area of a sphere, that would be the surface area, is equal to 4 pi r squared. then you realize that the total surface of a sphere is 4 pi times a steradian, or 4 pi times a radian squared. So that's how you can then convert to the area used in the unit of a candela or candle. So one candle is 1 over 683 watts divided by a steradian or radian squared, or about 4 pi is about 12, so 1/12 is the surface area of a sphere. Now, the conditions of that, of course, is that we use light at 540 times 10 to the 12 hertz, which is about the frequency, the common frequency of sunlight at about 555 nanometers. So that's the typical light coming from the sun. So under those conditions, that is the definition of a candela. So summarizing, again, the luminosity of a star is all the energy a star puts out. The brightness of a star is only the visible light portion that the star puts out. In the case of the sun, only 43% of the total. When that sunlight is received on the Earth, it makes it through the atmosphere, a portion of it doesn't make it through. So only about 1,050 watts per square meter out of the original 1,361 watt makes it to the surface of the Earth directly from the direct sunlight. A little bit more of it makes it through the scattering, also reaching the surface. But if we only take the direct sunlight and convert that to the brightness, we can say that 1 watt of sunlight, direct sunlight, produces 93 lumens. So we use the term lux, which is lumens per square meter. And so the amount of lux, the amount of lumens per square meter that the sun contributes, is 98,000. And then we can say that a lumen can be converted to a candela, the light coming from a candle. So 1 lumen is a candela per square radian, and a candela is about 1 over 683 watts per steradian. So those terms are usually not used very much, but in case you're interested, in case you've seen them and you don't know what they mean, here you have a pretty good definition of what they are, and hopefully that clarifies things for you. So we're going to continue defining brightness, luminosity, intensity in the next several more videos. Welcome to Lecture Online, and now we're going to take a last look at the comparison between luminosity and brightness. And the reason why I'm hammering on this so much is because we use the term brightness, unfortunately, interchangeably between the amount of energy we receive from an object far away and how bright it appears here on the Earth. We use the same term brightness in both cases, which is a little bit confusing. So let's say the official definition of brightness is in terms of what percentage of the total energy radiated from the object comes from the visible light. For example, we can say that the luminosity refers to all the radiation emitted by an object like the sun or a star, and the brightness refers to the visible light portion only of that radiation. In the case of the sun, the visible light portion is about 43%, and therefore the rest is emitted in the IR, infrared, and some in the UV. For Sirius, the portion is different. Only 26% of the total energy emitted from Sirius is in the visible light. A large portion of it is in UV and some IR. So the ratio then of the brightness to the luminosity for the sun, so in this case for the sun, the ratio in the case of the sun, that would be equal to 43%. So, and for Sirius, if we do the ratio for Sirius, the brightness ratio to the luminosity, and that's in the case of Sirius. Now, the letters that we use to indicate that would simply be B, small b for brightness, and capital L for luminosity. So that ratio for Sirius is only 26%. And so when we talk about brightness, we talk about the portion of the electromagnetic radiation that's being emitted from the star that's in the visible portion only. Now, we also talk about brightness in the intensity when it reaches the Earth. And that refers to the case where we talk about apparent magnitude and an absolute magnitude, the brightness and the bolometric magnitude. So what do we mean there? Well, the terminology apparent magnitude and absolute magnitude actually refers not to the total luminosity of the object, but to the brightness of the object, the portion that's in visible light only. And that's why there's some discrepancy when we start calculating luminosity and brightness of objects relative to how bright they appear to us here on the Earth. And there, we're going to try and clarify that in the next video to show you what we actually mean when we say apparent magnitude and absolute magnitude. Is it in terms of the total luminosity, or is that in terms of the brightness of the star in the visible light portion only? To clarify that, let's come back to the next video and take a look. Welcome to Lecture Online, and now we're going to take a closer look at what we mean with apparent magnitude. Apparent magnitude is a scale used in astronomy to determine the brightness that stars appear to be from our vantage point on the Earth. Now, they may be very dim stars are really close, very bright stars are far away, it doesn't matter. It's how bright stars appear to be. And also, when we talk about apparent brightness, we're really talking about how bright stars appear to the visual eye, to the eye of a person, which means since people can only see visible light, it's based upon the visual portion of the light that comes to us from these stars. Remember, most stars, they emit both UV and infrared as well as visible light, so there's three different kinds of frequencies that we receive from the sun. The total luminosity of a star is the total power output or output of energy from the star in all three frequencies, in all three wavelengths. But when we talk about the apparent magnitude or the apparent brightness, we're only talking about how bright stars appear from a visual light perspective only. We ignore the UV and the infrared. And so based upon that, we have a scale called the magnitude scale or the apparent magnitude scale, where smaller numbers means brighter and larger numbers means dimmer. And the way the scale works is that for every increase of one magnitude, the star will be either 2.5 times brighter or 2.5 times dimmer than the other star. For example, if we have star A with a magnitude or apparent magnitude of 2 and star B apparent magnitude of 7, since 7 is a bigger number than 2, star B is a dimmer star, or at least it appears dimmer to us, than star A. When we take the difference in the magnitudes, which is 5, and we then use that for the exponent of the number 2.512, 2.512 to the fifth power is 100, which means that star A is 100 times brighter, or at least it appears to us to be 100 times brighter than star B. So therefore we say the apparent brightness of star A is 100 times the apparent brightness of star B. And so it is 5 magnitudes brighter, or it appears 5 magnitudes brighter than star B. So what does it all mean? Well, it turns out that we have to somehow set the scale to a certain point where we can kind of reference ourselves. And it turns out that since Vega has an apparent brightness of almost 0 magnitudes, it's slightly over 0.03 or 0.04, we can say that this is probably a pretty good baseline. So we can say that 0, an apparent magnitude of 0 makes it as bright as Vega. So if an object is brighter than Vega, it will have an apparent magnitude less than 0. And if it's not as bright as Vega, at least it doesn't appear to be as bright as Vega, it will have an apparent magnitude greater than 0. So that's a pretty good baseline. Another way to look at it is we realize that the apparent magnitude of the sun is minus 26.7, somewhere in that neighborhood. So if we go way over here, and we go minus 26.7, that's the apparent magnitude of the sun. Now notice, what is the difference in magnitudes? Well, that's 26.7. And if we then take the number 2.512 and raise it to 26.7, so we have 26, that's 2.512 raised to the 26.7, we get a really big number, 4.4 or 4.79 times 10 to the 10th. And if we also realize that the brightness of the sun on the Earth is about 98,000 lumens per square meter, then if you divide this number by the difference in magnitude used as an exponent over here, for example, we take 2.512 and raise it to 26.7 power, we get something like 4.79 times 10 to the 10th. If we now divide this number into that, that tells us that an object that has 0 magnitude, like Vega, will give us a brightness measure on the Earth of 98,000 lumens divided by this number. So I'm going to do that. Take the inverse of that and times 98,000 lumens, and I get something like 2.045, roughly about 2.05 times 10 to the minus 6 lumens. Which means that if we have a star like Vega, which has an apparent magnitude of 0, that means the amount of light we get from that star is about 2.05 times 10 to the minus 6 lumens per square meter. That would be the apparent brightness in lumens for a star like Vega. If it's dimmer, it'll be less lumens. If it's brighter, it'll be more lumens. So that's kind of a baseline. Now, how do we actually measure the apparent brightness of a star? It's not like we kind of look at it and kind of estimate saying, I think that star is about this bright. What we actually do is we take a telescope and we put a filter on it. We have different kinds of filters. For example, we have a U filter, a B filter, or a V filter. There's other filters as well, but these are the three common filters. And the U filter allows UV light to come through, and it predominantly allows the 364 nanometer wavelength of UV to come through readily. The blue filter will pass by 442 nanometer light, and then the V filter, which allows yellow-green light to come through about 540 nanometers, allows the same kind of light to come through where the human eye is most sensitive to. So what we do is we take a V filter, put it there, so therefore we allow predominantly the visible light to come through and very little UV or very little infrared to come through, and then we measure the amount of lumens from that particular object, and from that we figure out the apparent brightness. And from the apparent brightness, we can then figure out the apparent magnitude. So that's how we measure the apparent brightness of a star. We use a special filter that allows visible light to pass through, holds back the UV and the infrared, and then we measure how bright it appears with a measuring apparatus, and then we convert that to an apparent magnitude. And that's how we find the apparent magnitude of different stars and different objects, such as galaxies or star clusters or nebulas and things like that. So that's how we figure out the apparent brightness and the apparent magnitude. And that's what we mean by taking another look at that. Now we have a pretty good understanding where that came from and what it means. And now we can compare that to what we do in the next video. We'll compare it to the absolute magnitude and other things such as that. That's how we do that. Welcome to Lecture Online, and now let's talk about how we compare the luminosity of one star to the luminosity of another star. And typically what we like to do is compare the luminosity of a star to the luminosity of the sun, since we're so familiar with our sun. Now there's one kind of danger point here that we may not get the exact answer, because when we talk about luminosities, we talk about the energy emitted on all frequencies and all wavelengths. And when we look at the brightness of a star, we typically use filters and only look at the visible light portion of the star. But for most stars, it gives us at least a reasonable comparison between one star and the other. So let's say that we have the sun, which is 1 astronomical unit away. The sun has an apparent magnitude of minus 26.7. And we then have another star called Epsilon Eridani, and it has a magnitude of plus 3.73, and it's at a distance of 3.23 parsecs. And we'd like to know how luminous Epsilon Eridani is compared to the sun. How do we do that? Well, here's our equation. We compare the luminosities, so we want to get a fractional value for the luminosity of Epsilon Eridani and compared to the luminosity of the sun, based upon how far they are away from us and based upon how bright one appears compared to the other. All right, distance-wise, what we can say is that it is 3.23 parsecs, so 3.23 parsecs. That's the distance to Epsilon Eridani, and then we have to multiply that times the number of parsecs, or the number of astronomical units in a parsec, which is 206,265, that's astronomical units per parsec. And so now when we cancel the parsec out, we have astronomical units, and of course we divide that by the distance to the sun, which is 1 astronomical unit. And so we have this fraction here, and then we have to square that. So now that compares the distance to the star divided by the distance to the sun. We square that number. Now we multiply that times the relative brightness, or the fractional brightness of the star we were looking at compared to the brightness of the sun. Now notice that the sun has an apparent magnitude of minus 26.7, and Epsilon Eridani has an apparent magnitude of 3.73. So what we need to do is first find the difference in the magnitude. So difference in magnitudes is equal to 3.73 minus a minus 26.7. So when we add that together, that's 29, that's 30.43 magnitudes. 30.43 magnitudes, that's the difference in magnitudes, at least the apparent magnitude. And then we take the number 2.512 and we raise that to the 30.43 power. When we do that, we get the following result. So we have 2.512 raised to the 30.43 1.43 power. And what do we get? We get 1.48 times 10 to the 12th. So this is 1.48 times 10 to the 12th. And of course, if we now compare the brightness of the star to the brightness of the sun in relative brightness, we then put the 1 up on top and the 1.48 times 10 to the 12th on the bottom, because the sun appears this much brighter than epsilon Eridani. All right, now we're ready to go ahead and multiply this out. 3.23 times 206,265. Okay, then we square that number and we divide that by 1.48 e to the 12th. And okay, there we go. The result is that the ratio of the luminosity of the star to the luminosity of the sun is 0.2, oh, might as well just call it 0.3, round it off, 0.30. If you take the inverse of that, so that would be equal to 1 divided by 3.334. And that's the relative luminosity between the sun and the star of interest. So what that means is that the sun is 3.334 times as luminous as epsilon Eridani by this calculation. Again, one caveat with that is when we talk about luminosities, we actually talk about the brightness of all the radiation that they emit. And of course, if the stars are not the very same type of stars, one will emit more visible light, one will emit more infrared light, and so forth. And so this is an approximate number, taking into account that there may be some difference in the total luminosity that we're not aware of unless we know exactly what type of star we're dealing with. So keeping it simple, in a simplistic manner, for let's say first year astronomy courses, you simply say this is good enough for us. The relative luminosity can be found by simply taking the relative distance, we square that, we take the relative brightness, multiply it together, and whatever ratio we come up with, that is the relative luminosity of the two stars. And that's how we do that. Here we're going to talk about what we call bolometric magnitude. What is that? Well, just a moment. First, we're going to take a look at what we mean with absolute and apparent magnitude. Apparent magnitude is, of course, how bright a star or a galaxy or something appears to be from our vantage point from the Earth. And absolute magnitude is equal to the brightness or the magnitude or the apparent brightness of a star when it's located at 10 parsec. So more mathematically speaking, we can say that the absolute magnitude, which is indicated with a capital M, and the apparent magnitude, which is indicated with a small m, we can say that the absolute magnitude is equal to the apparent magnitude when the distance to the star is 10 parsecs. Or another way of saying that is, if we were to place the star in question at the distance of 10 parsecs, how bright would it appear? What would be the magnitude of the star? What would be the apparent magnitude of the star? And that will then be the absolute magnitude. So if you want to know what the magnitude is or the absolute magnitude is of the sun, we then imagine what it would look like if we placed it 10 parsecs away. So if we place our sun 10 parsecs away, the magnitude of the sun, the apparent magnitude, would be 4.83, and therefore that's the absolute magnitude of the sun. So, for example, if the sun were placed at a distance of 10 parsecs, which is 32.6 light years, the apparent magnitude would be equal to 4.83 of the sun with the distance equals to 10 parsecs. So since the sun would have an apparent magnitude of 4.83 if it was placed at a distance of 10 parsecs, we call that the absolute magnitude. So therefore, the absolute magnitude of the sun equals 4.83. That's what it would look like if it was 10 parsecs away. Now, the bolometric magnitude is something similar to that. First of all, what we can say is that these magnitudes, the apparent and the absolute magnitude, are based on only the visible light that we receive from the star. So what we do is we observe this with a telescope, and then we put a filter on there. Typically, we put a filter that allows visible light to pass through and blocks out infrared and blocks out UV. And so only the visible light gets through, and so we base the apparent magnitude and therefore the absolute magnitude on just the visible light we receive from the star. So a star who predominantly puts out visible light will appear brighter than a similar brightness star which puts out much more infrared and a lot less visible light. But sometimes we're interested in the apparent brightness for the whole perspective of the entire spectrum. So we're not going to limit ourselves just to visible light. We also want to know how bright the star appears to us, or how bright the star actually is, based upon its entire spectrum, UV, visible light, and infrared. So if we then allow all of the light to come through, all the various frequencies and wavelengths, then we want to measure the total luminosity of the star, then how bright it appears to us, and based upon that we give it the apparent magnitude and the absolute magnitude. And then we're talking about what we call the bolometric magnitude. That simply means that instead of just looking at the visible light, we want to see the brightness of the star in its totality of all the various wavelengths. An example of that is the two stars. For example, we have the star Sirius, which is a relatively small star. Well, it's bigger than average. It's a little bit bigger than the sun. It's a little hotter. It's a whitish looking star, and it puts a lot more UV and visible light and not as much infrared. Then we have the very large star Betelgeuse, which is a red giant. Now, I didn't quite draw the relative size of Betelgeuse. Betelgeuse would be bigger on the whiteboard compared to the Sirius being this big, but it's such a large star that it puts out an enormous amount of energy, enormous amount of luminosity. But the vast majority of that luminosity is in infrared, and very little visible light and UV are being emitted by Betelgeuse in comparison to the amount of energy it radiates in the infrared, simply because it's a very large star and the surface is relatively cool compared to the surface of Sirius. Nevertheless, since it's so big, it puts out way more energy than Sirius does. Yet, the absolute magnitude is, or the apparent magnitude, I should say, of Betelgeuse is less than the apparent magnitude of Sirius. But if we were to look at the bolometric magnitude, meaning taking all of the radiation into account, including the enormous amount of infrared radiation that Betelgeuse puts out, then Betelgeuse would have a much greater, a much brighter apparent magnitude than Sirius. And so that's why we use the term bolometric, which means including all frequencies. It's a term that's not used very much in beginning astronomy, but you might run into it sometime, and you may also need to realize that yes, apparent magnitude only deals with visible light. Bolometric magnitude deals with all of the light, all of the energies we get from a star, and we may get a different picture because, let's say, big red giants, they put lots of energy at the infrared, and so we account for that when we talk about bolometric magnitude. And that's how we do that. Welcome to Lecture Online, and now we're going to talk about another property of stars, which is called their surface temperature. And there's a relationship between their surface temperature and their color. So let's say we have three stars, star A, which is a very small reddish looking star, star B, which is a larger, kind of like our sun, a yellowish orangey looking star, and then let's say we have star C, which is a very big blue star. The colors are associated with their temperatures, and the temperatures associated with the types of radiation that we get from the stars. So when we look at the radiation curve from a star like star A, a very small red star, we find that the majority of the radiation is emitted in the infrared band, and the peak of the radiation occurs at a much higher wavelength, much longer wavelengths, for example 950 nanometers. The visible light spectrum here is just towards the left of the spectrum of the emission. Remember, all stars emit radiation like a black body, and so we have this typical radiation curve, and you can see that the predominant radiation for a small red star is in the infrared, peak wavelength 950 nanometers. For a star like the sun, the peak wavelength falls in the visible light range, and in this case, for example, let's say 600 nanometers, which is very close to what the sun puts out. And you can see that there's some UV radiated and some infrared, but at the center where the greatest amount of radiation falls is in the visible light range. Then if we look at star C, where the star is a big blue star, you can see that the radiation curve shows that there's much more radiation, they're much more luminous, and that a very large portion of radiation falls in the UV radiation. The visible light spectrum is over here. You can see that the peak occurs not in the visible light spectrum, but in the UV spectrum, and let's say that the peak wavelength is at 200 nanometers. Now, because of Wien's law, we're able to relate the temperature to the wavelength of that peak radiation. All we have to do is take the number 0.029 and divide it by that peak wavelength, and we actually get the surface temperature of those stars. So let's try it. For star A, the temperature of star A is therefore equal to 0.0029 divided by the wavelength, which would be 950 times 10 to the minus 9 meters. And so that will give us a temperature in Kelvin of, see, 0.0029 divided by 950 e to the 9 minus equals a temperature of about 3050 degrees Kelvin. So that would be one of those smaller redder stars. Star B, so temperature of B, would be equal to 0.0029 divided by 600 times 10 to the minus 9 meters. That's 600 nanometers. So we get 0.0029 divided by 600 e to the 9 minus. And we get a temperature of, let me try that again. That didn't look good. 0.0029 divided by 600 e to the 9 minus. And so the temperature of this one would be about 4,833 Kelvin, which is appropriate for kind of an orange-looking star. Next, we go to star C. So the temperature of star C is equal to 0.0029 divided by 200 times 10 to the minus 9 meters. And that star, let's see here, would have a surface temperature of 0.0029 divided by 200 e to the 9 minus. And we get 14,500, so 14,500 Kelvin. So notice with Wien's law, it's fairly straightforward to be able to tell the surface temperature of stars simply by realizing and measuring where the peak radiation lies. Small red stars in the infrared, medium-sized stars like the sun or smaller than the sun would be in the visible light range, and finally star C would be a very big, very bright and big blue star with peak wavelength in the UV radiation band to the left of visible light, and those are very hot stars, as you can tell. So Wien's law, very handy way of telling how hot the surface temperature of a star is. Welcome to Electron-Line, and now let's take a look at what we call UBV photometry. What that means is that we try to measure the brightness of stars based upon their color, and determine their color is not as easy as you might think. You know, we look up and say, oh, there's a red star, but it's not that easy. We want to know exactly the color of that star so we can find the exact temperature and size and so forth of the star. The way we do that is we take a look through a telescope at the same star using various filters. And the three most common filters we use are what we call the UBV filters. The U filter is a filter that predominantly lets through UV radiation, especially at the 364 nanometer range and beyond, and a little bit on both sides of that wavelength. The B filter predominantly lets through blue light, mostly at the 442 nanometers and a little bit plus or minus on that. And then we have the V filter, which predominantly lets through the visible light, and it's centered around the yellow-green color at 540 nanometers, which is a color that the human eye is most sensitive to. So what we do is we take a look, let's say we take a look at the star right here, and we measure the light come from the star with the V filter, the visible light filter, and we find out, relatively speaking, for that star, because it could be far away, it could be close, it could be a large star, it could be a small star, it doesn't matter. We're not comparing the intensities or the brightnesses of the individual measurements to the other stars. We're simply comparing it to the measurement on the same star with a different filter. And so if we look at it with a visible filter, even though most of the radiation is in the infrared band, relative to the light coming to us from that star with the blue color filter or with the UV filter, it has a high throughput. A lot of energy comes through the filter when we use a visible filter, relatively speaking. Then we look at the same star again with a blue filter, and we find out the amount of energy coming through the filter is much lower. And then finally we try to measure the intensity coming from that star with the UV filter, and we find that very little UV actually comes from that star. So then what we do is we find the ratios of those. So we compare the ratio, the brightness with the visible filter divided by the brightness with the blue filter, and we find that that ratio is very large. That ratio is greater, and I shouldn't put an equal sign there, simply that ratio is greater than 1, which means we get more energy in the visible light spectrum than we do in the blue light spectrum. And then if we compare the brightness in the blue spectrum divided by the brightness in the UV spectrum, and again we find a ratio greater than 1. If that's the case, we then conclude that it is more of a reddish looking star, a star more to the right of the spectrum, more to the infrared and the red. And so depending upon how much greater is than 1, we can find out the exact color with these two ratios right here. If we now look at the second star and we find that we look at the ratio of the light coming through at the visible light spectrum versus the blue light spectrum, so we get B of V divided by B of blue, well, we find that the ratio is greater than 1, but not quite as great as this one. So maybe we want to write it like this, that this ratio is much, much greater than 1, this ratio is somewhat greater than 1, and that's how we can tell the difference between a blue star and one that's more orange or yellow in color. Then if we measure the light throughput at the blue, with the blue filter compared to light output with the violet filter, again we find that this ratio is greater than 1, and so therefore we can conclude, based upon these ratios, what type of star we're dealing with. Finally, when we look at a very bright blue star, we take the ratio of the visible light spectrum compared to the ratio of the blue light spectrum. In other words, the amount of light coming through at visible light versus light coming through only at the blue light, and we find that that ratio is less than 1, which shows that the highest intensity falls to the left of visible light. And so you can see that the blue spectrum would have more intensity than the rest of the visible light spectrum. So we find a ratio less than 1. And then if we compare the light coming through with the blue filter compared to the light coming through with the UV filter, again, we find out that that ratio is also less than 1, which would then indicate if both of those ratios are less than 1, we're probably dealing with a very bright blue looking star or a very hot white star. And again, that's how we determine the exact color. Now, we haven't done justice yet with how we exactly pinpoint the exact color and therefore the exact temperature of the star, but once we put the real ratios in there, we'll get something that looks very close to what we're used to using with this kind of what we call UBV photometry. Here we just want to get the feel of how the mechanism works. Simply, we can tell what kind of star we're dealing with by simply looking at the star with 3 different filters, finding the brightness ratio using the 3 different filters, and then based upon the outcome of that, we can see that we're dealing either with a red star, orange star, blue star, or a star that is so hot that it puts out a lot of UV radiation. And that's how we do that. Okay, welcome to Lecture Online, and here's our second video on what we call UBV photometry. Here what we've done is set up a table to get a much better feel for how this works. Again, the different kind of stars have different kind of emission spectra, and you can see that the very cool stars that have low surface temperatures have spectra that are predominantly in the infrared. The medium level stars like our sun and orange level stars have much more of the emission in the visible light spectrum, and then the very big hot stars that tend to have most of their emissions in the UV spectrum. So how do we figure that out? How do we measure the color of stars, which is harder to do than you would think? We do that by using a 3 filter system. We have the UBV filters. The U filter predominantly lets through UV radiation centered at 364 nanometers. The blue filter lets blue light predominantly through, centered at the 442 nanometer range. And the visible, the V is for visible or yellow-green light, which is basically the light that our eyes are most sensitive to, is centered around the 540 nanometers, meaning that those filters allow that type of light or that type of radiation to pass through more easily than the others. It blocks out the others. So when we look at these various examples of stars, some of the more famous stars, so Bellatrix is one of the stars in Orion, which has a surface temperature of 21,500 degrees Kelvin. Pretty hot. Notice the ratio BV to BB, meaning it's less than 1. You can see that the energy of the blue light range is much stronger than the energy of the rest of the visible light spectrum, so therefore we have a ratio less than 1. And then we can see that the energy coming through at the UV spectrum is much greater than the energy coming through at the blue light spectrum. So the ratio there is far less than 1. This would indicate a very hot star, probably with a very dark blue color. Well, I shouldn't say dark blue because they don't have that dark blue color, but definitely a strong blue color associated with that type of star. The next star, Regulus, which is the brightest star in the constellation Leo, with a surface temperature of 12,000, has a ratio of the visible light spectrum to the blue light spectrum of 0.9. That's a little higher than 0.81. So that means a little bit more of the visible light is coming through relative to the blue light. And you can see that the ratio of the blue light to the UV is not as not as small, you could say. In other words, the UV radiation is not as predominant compared to the blue radiation, which you can then see that it shifts a little bit more from the blue towards the visible light spectrum, and therefore associated with a blue-white color, and therefore associated with a lower surface temperature. The next star is Sirius, the brightest star in the sky, also the brightest star of the constellation Canis Major, surface temperature of 9400. Notice that the ratio of the visible light to the blue light is 1:1. And the ratio of the blue light to the UV is almost 1:1 as well, meaning a slightly higher UV band or UV radiation energy than blue energy. And that then indicates that it's a whitish looking star. It's kind of like white blue. But again, Sirius, when you look at it, it's a very bright star and has this whitish color to it. Megrez, which is one of the stars in the constellation Ursa Major, or the Big Bear, you can see a surface temperature of 8630, excuse me, with a ratio of visible light to blue light now greater than 1, meaning that it's now more shifted towards the visible light. Visible light is coming in a lot stronger and has more energy at the visible light spectrum than at the blue light spectrum. And notice that it has more energy at the blue light spectrum compared to the UV spectrum. So therefore, it's shifting away from having the predominant energy in the UV to the predominant energy in the visible light. So you can see that it's beginning to shift over. And then the color of Megrez is also whitish looking star, still pretty hot. Then the next star, Altair, which is a star in the water bearer, which is at 7800 surface temperature. Notice that the visible light spectrum is now quite a bit stronger than the blue light spectrum, and the blue light spectrum is stronger than the UV light spectrum. So again, that shifts it more into the visible light spectrum, and from white now it's going to the yellow-white color. Then we go to our sun. We know where our sun is, surface temperature 5800 degree Kelvin. Notice how much more we get energy through at the visible light spectrum compared to the blue light spectrum, and how much more of the blue compared to the UV, which then indicates, since this ratio is much greater, this one doesn't change as much, but this ratio is much greater, we know that it shifts more into the visible light spectrum, and therefore it's associated with the yellow star like our sun. So next star here is Aldebaran, which is the bright star in the constellation Taurus, 4000 degrees surface temperature. Notice the large ratio of visible light brightness to blue light brightness, which means it really has shifted over into the visible light away from the UV and the blue light. And notice a very large ratio again from the blue to the UV, meaning very little UV coming through, which we know causes it to shift it quite a bit to the right of the spectrum, quite a bit to the reddish orange color, and so therefore that star is indeed an orange looking star. And finally, Betelgeuse, that very large star in the constellation Orion, surface temperature 3500. We know this is a big red giant. Notice the ratios for visible to blue and blue to UV. Visible to blue is very large, meaning it's very far to the right, far away from blue, meaning into the red region, and blue to UV, meaning that there's almost no UV radiation coming from that star. Therefore, this is a very large ratio. Therefore, we know the color is red with a very low surface temperature. And that's how we use those three filters to determine the exact color, the exact wavelength predominantly that comes through from that star, and from that we can determine the surface temperature of the star and many more things, which we'll learn in some later videos as well. So hopefully this gives you a really good idea of how we use UBV photometry to determine the color of stars. That's how we do that. And the light. Welcome to Lecture Online, and here's our third video on what we call the UBV photometry. And notice again, just as a summary, we have three filters that we use. A filter that predominantly lets through what we call ultraviolet radiation, centered around 364 nanometers. The blue filter predominantly lets through blue light, and not so much the rest of the visible spectrum or UV spectrum, centered around 442 nanometers. And the V stands for yellow, green filter or visible light filter, predominantly centered around 540 nanometers, which is the wavelength that our eyes are most sensitive to. And then when we look at the light of a particular star with the three different filters, and then we calculate the ratios of the intensity of the brightness coming through to us, we can see that for Bellatrix, we have a very low ratio between, and this should be, the ratio between the visible light coming through and the blue light coming through, because much of the spectrum is shifted towards the blue and the UV radiation. So when we have a small ratio between the visible light brightness versus the blue light brightness, we know that it must be a very hot star. In this case, Bellatrix at 21,500 surface temperature in Kelvin. But take Sirius, for example, the ratio is exactly 1:1. In other words, we have the exact same brightness at the visible light spectrum compared to the blue light spectrum, which means that it's shifted towards the left band of the visible light spectrum, and therefore we know the surface temperature is 9,500. And then finally, as an example, the Sun, which has much larger brightness at the visible light spectrum compared to just the blue light spectrum, and therefore we know that it's a cooler star with a surface color of about yellow star, and the Sun at a temperature of about 5,800 degrees. Now, if we put a lot more stars in there, you can see that we come up with this very nice curve right here. And so that makes it really easy in the future to look at any star, find the ratio in the brightness of visible light to blue light, find the location on that curve, and then we have the associated surface temperature along with that, and the specific color that that star is at. So that's how we use what we call UBV photometry. We use the 3 filters. We look at the brightness of the star with the 3 filters. We do the ratios, not just visible to blue, but also blue to UV radiation. And from that, we can pretty well nail down the exact temperature and the exact color of the star. And that's how we do that.